I'm really excited to be able to share this with you online, and at least if we have to be online, it means that all the interstate people can join in as well. So that's an upside. I would like to acknowledge that I'm coming to you today from the traditional lands of the Wurundjeri and Bunurong people of the Kulin Nation, the unceded lands, and pay my respects to their elders past and present. A little bit of housekeeping. For the most part, you will probably be trapped on mute unless you ask a question at the Q&A. That's to make sure we don't get echo and feedback and nasty things like that. And there will be plenty of time for Q&A. So please be ready to ask me anything and give me a really hard time. That's what this is all about. Please share things that you find interesting from today on any form of social media you like, and with people face to face, if that's an opportunity for you. And use the hashtag Raising Heretics if you remember. That would be awesome. Huge thanks to Michelle and Skills Matter for providing the Zoom for us today and doing the technical wrangling on my behalf. We're really lucky to have the amazing Dr. Nikki England here to kick things off. So welcome, Nikki.
Hello. It is my absolute pleasure to join this event, let alone get to introduce the amazing Dr. Linda McIver. Lynn, we first met, I was thinking about it, probably a dozen years ago at a CS for HS event in Melbourne. And my first vivid memory of you is huddled at the coffee cart, essentially, in the cold, talking vehemently about how best to engage teachers with data science and computer science, and how to get their students excited about really digging into the science of data and finding answers and questioning more. And so it has been my absolute pleasure over the last decade to watch that passion of yours grow into, well, into physical form manifested in the pages of a book. We got to know each other much better through the Superstars of STEM program, which is a fantastic program. And watching you take those first tentative steps of, what am I doing? Am I going to found ADSI? Am I going to change the world? And it's been my absolute pleasure to cheerlead you on from the sidelines and watch you do just that. I'm sure everyone here knows about ADSI, but for those of you watching the fantastic recording, go and check it out later. So ADSI was started in 2018. Or what did you say? Several lifetimes and 3 years ago. It certainly feels like that. They do fantastic work. You do fantastic work. This book, hopefully, will inspire so many more people to keep doing that fantastic work. And it's my absolute pleasure to introduce you here and to hear all about it.
Thanks so much, Nikki. That was awesome. So I want to give you a bit of an intro to why I started ADSI, why I wrote the book, why I think all of this stuff matters. And then I'm going to give you a bit of an excerpt. I'm going to do a reading from chapter 3, which has the heading Science is Solved, which, by the way, Nikki came up with. I should add, I'm terrible at naming things. So all of the good names, like the name of the book, came from somebody else. My friend Kathy Meyer gave me the idea for the name of the book, and it's wonderful. It's perfect. So I have a PhD in computer science education. I was an academic for a surprisingly long time. And then I felt like all the research I was doing in computer science education wasn't translating into the classroom, wasn't really having an impact. So I went into secondary education because I felt like I was going to have more of an impact there. And while I was doing that, I was teaching 2 subjects. I was teaching a year 11 subject, which was computational science, really, and it was my own and Victor Rajewski's design, and we got to do what we considered the interesting stuff. We basically designed it from scratch, and it was a wonderful opportunity to do real things. And the capstone project in that subject was a computational science project where the kids worked with scientists to meet their data and computational needs. And over the years that we ran that project, we learned a lot about what works and what doesn't work. Eventually, we zeroed in on data projects because they give such a wonderful scope for for something that engages beginners, but also something that the really advanced kids can really fly with. And even in the first year we ran that project, while we were still trying to figure out how it would work, we had students continue working on the assignment the following year. And that turned out to be a theme. It happens nearly every year that we had kids keep working on the assignment long after the subject was finished, sometimes after they'd left school. And the trick was they were doing something real. They had the capacity and the power to contribute to real research. So in that first year, they did cancer research. And I was like, well, year 11's doing cancer research. I'm done. Like, I cannot top that. That was just insane. But, you know, it just went from strength to strength. And in the end, we did projects from psychology through to astrophysics, and didn't really matter what the topic was. What mattered was the opportunity to do something real. Nikki calls it computing with purpose, which is just the perfect phrase. It gave them the motivation and the engagement to really really fly. And at the same time, I was teaching a year 10 subject, which was not my subject, and it was computing with toys. It was drawing pretty pictures in Scratch. It was pushing robots out of circles and making them follow lines, and it was all the fun stuff, which was super engaging and would get the kids into it. And the single most common piece of feedback I was getting was, why are you making me do this? I do not want to do this. It is not relevant to me. And by the way, I hate it and it makes no sense. And these were interfaces designed for kids, so they should have been easy to use. They were not, but they should have been. So eventually I managed to persuade the leader of that subject to trial a small data science unit. And we used an election data set. We downloaded a spreadsheet file which had all of the votes for the Senate, for Victoria, for the federal election. And so that was over 3 million lines of data, and you can't even open that in a spreadsheet, which meant they had to code, which of course was my goal, but you know, they had a reason now to learn to code instead of trying to push robots out of circles and make them follow lines and draw pretty pictures. Yeah, very sneaky. And the shift in their attitude to that subject was astounding to me. Like, I knew it was going to be better than the toys, but I had no idea how profound the impact was going to be. We were teaching the same programming skills, the same underlying concepts with a few more. So there was a fair bit of data literacy in there, like looking at graphs and saying, well, where's the zero on that scale? And is this a valid representation of the data? Is it trying to pretend that the data is something it's not? Those kind of questions. But mostly it was the same programming skills, but just in the context of real data. And it was messy data, because turns out people are very bad at following rules, and those votes did not follow the rules at all. So you'd explain the Senate voting rules to the kids, and you'd be like, okay, people can vote above the line or below the line, but not both. And so they'd be like, great, so there'll only be numbers in this section or this section. I'm like, I wish that was true. No, that will not be true. And so, you know, they had to deal with the fact that the data was not what it should have been, and it was messy, and it was ugly, and it was complicated, and they loved it. It was insane. There were so many problems with that first instantiation of the subject. We did not have enough teachers to teach it who really had the skills. So I was trying to be everywhere all at once, which is something of a challenge. But they loved it. I mean, we'd had the same problem with the toy version, right? We still didn't have enough qualified teachers. But because the kids could now see the point, they were much more forgiving, they were much more engaged, they were much more interested. They would come to me and go, oh my God, this is so useful. I'm using this for my science assignment. I'm using this here. And I saw this graph on the news the other day, and oh my God, there wasn't a zero on the scale, and it was outrageous. And all of those conversations were replacing the ones that were like, why are you making me do this? So I figured I'd solve the problem of getting kids involved in tech, which is why I quit. I did that for a couple more years with different data sets. It didn't matter which data set we used, as long as it was real, it had the same effect. And the reason I quit was because I wanted everyone to be able to do this, not just the kids in my classes. And I realized that while I was teaching, I was not going to have the time or the energy to spread it. Also because the only reason I could do these projects was that I was part-time. So I could use my own time to find the data sets, make sense of them, figure out how they worked and what they meant, and build projects around them. It's pretty time consuming. And that was for me with a PhD in computer science. For your average digital technologies teacher, just completely out of reach. So I thought, what if I could provide the projects? What if I could train the teachers? What if I could get them over that sort of huge learning curve and the time needed to construct all of this stuff, and just get them straight into the work and get them engaging the kids? And you know, for the most part, we don't teach the teachers to code, because if I walk into a room full of teachers and say, I'm going to teach you Python, there'll be a whisking noise and I'll be like, where did everybody go? There are certainly teachers who are ready for it, and there are teachers who are doing it already, but we don't have the coverage for every digital technologies teacher in every school to be doing that stuff. They just don't have the skills yet. They will have, give me a week or two, but they don't have them yet. So yeah, so I started the Australian Data Science Education Institute, and the goal there is to, as I said, to train the teachers, to build resources so they don't have to find the resources themselves, but also to spread the word, to get this idea out there, to change the way we train teachers at the start, to change the curriculum, to change really quite a lot of things about education. And when I started ADSI, I thought it was to get kids engaged with tech, but actually it turns out it's a lot more important than that, because a lot of what we do is we ask questions like, what's wrong with this data set? Because no data set is perfect. So how is the data not quite the data we need? It's just the data that we have. What's missing from the data? Who's not represented by this data? Who is overrepresented in this data? Questions that if the tech and data science industry asked more often, things could be very different. You may have heard about Google's image recognition program, which had been trained exclusively on white male faces and identified people of color as gorillas. Those kinds of things should not happen, and they would not happen if people were looking at training data sets and saying, what's wrong here? What's missing? So the goal is teach the kids those critical thinking and data literacy skills from the start. Teach them to question the results of other people, but almost more importantly, teach them to question their own results. Teach them that there's no such thing as a right answer. There is an answer which has good points and bad points, and let's evaluate your solution and figure out where it works, where it doesn't work, who's left out, who might be harmed by this solution. So we've got kids doing real projects and making change in their own communities. They're doing things like looking at the litter in the school grounds and using data science to measure it and try to fix it and evaluate to see if their solution actually worked. To look at things like usage of playground equipment. Is it fair? Are there people who never get a chance at the basketball hoops or at the slides, or things like that? So they're looking at problems in their own environments and bigger problems in the broader community, in the global community, and they're measuring them, they're evaluating them, they're trying to make change, and then they're measuring to see if the change worked and to see how well it worked and how well it didn't work. Where did it fall down? Which is something I would really love to see governments do more of, to see business do more of, and to see education do more of, because evaluating our solutions turns out not to be the standard. So that's just some of the reasons why I needed to get all this out, and I needed to write the book to try to spread these ideas and also to get people challenging them. So this is in many ways my life's work. This is the distillation of my expertise down into what I see as a blueprint for fixing education. But I'm handing you something precious here. I don't want you to treat it carefully. I want you to tear it apart. I want you to challenge it. I want you to really go into the ideas and come back to me and go, this is not going to work, or this one's great, but, or whatever your response is. I want to hear it. I want to start the conversation. I want people to really engage with these ideas and figure out what works and what doesn't work, and better them, improve on them. make me look dumb. I don't care. Let's just actually have the conversation. So that's the goal with the book. I'm so excited to have had so many pre-sales already. That's amazing, and it's now out in the wide world. It's available on Booktopia and Amazon and all of the places you normally buy your online books. It's an ebook and a paper book. So if you like it, if you think it's worth reading, if you think the ideas are worth engaging with, please tell your friends. Please buy them a copy of the book or tell them to go buy a copy. Shout about it on social media. I don't care whether you shout the ideas are terrible or you shout the ideas are great. Just have the conversation. I do care, that's a lie, but I want you to engage with it. That's the point. Just before I go into the excerpt that I'm going to read, I want to do a quick shout out to just some of the people who made this possible. You'll have to read the acknowledgements for all of the people, and it's 2 pages long because there were a lot. I've been incredibly lucky in the support I've received. But I want to give a particular shout out to my family, who have had to live with someone writing a book and tearing her hair out and cursing and swearing and doing all of those things for quite some time, and getting really angry about some of the examples. When you read the book, you'll understand why. And obviously my former students, like, I would never have done any of this if I hadn't had the generous cooperation and collaboration of those amazing students, many of whom I'm still in contact with today, and they're just an absolute delight. So a huge thank you to them. Obviously, the Unbossables, you know who you are, we've had a chat most work days for the last 20 years of the pandemic, and it's been a literal lifesaver. My twin, Robin, I know you're on there somewhere, couldn't even have survived without you. And my big brother, Mark, who has been very patient and generous support over the last couple of years. And also to Tia Lowenthal, who designed the cover, which I just love. I'm so thrilled with the cover. It's amazing. For someone who teaches visualization, I cannot draw to save my life. So I'm thrilled with the cover. So this is an excerpt from chapter 3, which is titled Science is Solved. And the heading of this section is Science in Schools and Education in Confirmation Bias. Far back in the ancient mists of time, when my husband studied year 12 biology, and I'm allowed to say that because I did year 12 in the same year, there was a question that caused some controversy. True or false, all autotrophs contain chlorophyll? Now, according to the year 12 curriculum that year, the answer was true. Every creature that creates its own energy uses chlorophyll to do it via the process known as photosynthesis. The trouble is, in the real world, the answer is false. It turns out that there are teeny tiny beasties that live around volcanic vents in the deepest, darkest recesses of the ocean, among other extreme environments, that use a process called chemosynthesis, using chemical reactions to fuel their food making. And this is one of the gotchas that teaching science as facts leads to almost inevitably, because the world is complicated, and teaching facts according to the theories you're up to in the curriculum is quite likely to fall foul of what we know according to more complex models that we haven't taught yet, or that were only discovered this year, for example. So we wind up assessing according to what's in the course, rather than according to how the world actually works. And it's worse than that, because when we teach facts and known processes, we encourage students to get the expected answers. So school science experiments generally involve known inputs, known processes, and known outputs, and they're often assessed as reports that are required to contain the expected answers. So this means that students are doing experiments where they know the results they expect to get, and they know they will be assessed according to whether they got those results or not. Consider a chemistry experiment that involves taking a fixed amount of reagent A, adding it to reagent B, and measuring the time taken for the reaction to finish bubbling at, I shouldn't look at the chat, at different temperatures. Students get results and produce a graph, but it doesn't look right. What do? In a world where science education was explorative and based on understanding, perhaps the students would be able to explore why they got different results. Maybe they would repeat the experiment with the same equipment, but also with different equipment to see what happened. Maybe they'd test the reagents or recalibrate the thermometer to try to figure out what really happened. In practice, there's very rarely time for this. Typically, they adjust the graph until it looks right, changing their data as necessary, often because the marks for the experiment hinge on the report that contains the expected results. So we're teaching them to achieve a known outcome. In other words, we're teaching them confirmation bias. If you don't get the result you expected, change it until you do. This is the absolute opposite of what science should be about, which is fallibilism. And yes, exactly why p-hacking is so common, Laura. Fallibilism is about proving doing everything to prove your theories wrong, rather than trying to prove them right. And that's what science should be. It should be testing things and trying to prove them wrong. It's not teaching our kids to test and be skeptical and to explore what happened when they got unexpected results. It's teaching them to get the right result. As I said, that's just confirmation bias. So lest you think this is a needlessly cynical view of science experiments, consider this story. A thermodynamics experiment conducted by a physics teacher friend of mine over Zoom last year during remote learning produced unexpected results. So the experiment was take a cold thing and a hot thing, put them next to each other, and the temperature should equalize. That's what thermodynamics says should happen, which indeed happened, but the temperatures actually crossed over a little bit. So the cold thing wound up a little bit hotter than the hot thing, and the hot thing wound up a little bit colder, and that shouldn't happen. They should get to equal and stop. So my physics teacher friend was really excited. She was like, this is great. This is so interesting. We can really dig into this. You know, was it the equipment? Was it the conditions? Was there some flaw in the way we measured it? It could have been the basis of a wonderful conversation about testing theories, about data, and about exploring the unexpected. The trouble is, the curriculum effectively demands that the results be sanitized so as not to confuse the students. All of the teachers involved in that course, which I think was year 11 physics from memory, all agreed that the best thing for the students was to delete the anomalous results. And, you know, they weren't wrong, because the goal of that subject was for the kids to get good results, which is in itself a huge, huge problem. So taken together, this all means that we're teaching confirmation bias, not science. And then we wonder why the public is uncomfortable with the evolving understanding that characterizes good science. That's the end of the excerpt. But I'd just like to add to that, if you think about the issues we're having with vaccines and with our understanding of COVID, and people going, but science has now changed what it's saying about COVID, that means science is wrong. You realize that actually science changing its understanding is right. There's still a surprising number of people sticking around, and I'm really grateful to you all for showing up and for your enthusiasm for the book, for the number of copies I've already sold, and the number of you who bought multiple copies and all that good stuff. Please, as I said, engage with the ideas in the book, challenge them, talk about them, tweet about them, Facebook them, get in touch with me, tell everybody, let's get the word out. If we want to change the world, it's up to us to spread the word. So let's create the momentum and make change. Thanks so much for showing up. You're all amazing.